మేము వేసుకుంటామండి మరి మాకు తగ్గుతాయి తగ్గుతలేదు మరి మీ అమ్మాయికి
Okay, good morning to my dear students. So previously we have discussed about transformation matrix of two coordinate frames. So this is a transformation matrix. So this is a transformation matrix. So we have discussed in the last class. So which is very, very important to know the position and orientation of a coordinate frame with respect to the another frame. So this notation 1T2, it actually represents us. So this coordinate frame 2, the position and orientation of this coordinate frame 2 with respect to coordinate frame 1. Okay. So this transformation matrix, which has 4 parts, So the one is 3 by 3 matrix, which denotes rotation or orientation of the coordinate frame 2 with respect to frame 1, and 3 by 1 matrix, that is column matrix at the rightmost 3 elements in this matrix. So this is denoted as 1D2. It represents a translation vector. Okay, or it actually denotes the position of that frame 2 with respect to frame 1. So zeros in the bottom of this matrix, so this 1 by 3 matrix, it is denoted as a perspective matrix. It is used for vision systems. And there is no vision systems, so it is the elements in this matrix are 0, 0. So finally, the last part in this matrix is 1. It denotes scale factor. So in industrial robotics, so we always take this scale factor as 1. Okay, let us move to the next topic. So in short form, the transformation matrix is denoted as like this in short form. Okay, so this is say an equation of a vector of point P with respect to frame 2. So this is equal to 2T1 P. So it is actually inverse of the above equation. So the above equation, which is for the point, the description of point P with respect to frame 1 is equal to, so 1 transformation matrix 1 T2 2P. So this is the equation we have seen in the above. But this equation, so this equation for inverse of this equation. So inverse of the first equation. Okay. So this 2T1, it is the inverse of 1T2. Okay. So now let us discuss how to describe an object which is in space. Okay. So before we discuss the position and the orientation, so an object in industrial robotics, so the object is picked by an industrial robot by its end effector, you know. So how to describe that object in 3D space? So when it is completely specified, so the location of object is completely specified in 3D space by describing its position and orientation. By its position and orientation, then only we can say that that object is specified fully or completely. Okay. So let us consider a body, a general body, as shown in this figure. Okay, so this is a general three-dimensional body, which is in space XYZ. Okay, so which is away from the origin of the frame O. So first of all, let us assign a coordinate frame to this object. Okay, so that coordinate frame. So here we consider it as a frame 1. The axis of this frame 1 are U, V, W. So the origin O1, which is away from the origin O of XYZ. Okay. So now we have to describe the object frame UVW, its position and orientation with respect to the frame 0th frame XYZ. Okay, so that is the specification of the object completely in 3D space. Okay, position and its orientation. So here we need to discuss. First of all, we need to discuss the how to convey how to convey how it is attached to the end effector. So what are the vectors which are involved in the end effector? Okay, so there are three vectors which are known as normal vector, sliding vector, and approach vector. By using these vectors, we can convey the frame which is assigned to the end effector, So, so here it moves according to the wrist, according to the motion of the wrist. So earlier we have seen the motion of the wrist, which are in 3 degrees of freedom. They are known as yaw, pitch, and roll. Okay. So yaw, pitch, and roll are the wrist motions. According to these motions, so the end effector can be moved in a space, and also it can the end effector can grab the or can pick the object in 3D in space. Okay. So now let us see how to convey those three vectors to the end effector. So let us look at the figure as shown in below. Okay, so this is an end effector. Okay, it consists of three. To this end effector, first we need to assign a coordinate frame. Okay, so this is a coordinate frame. Okay, it consists of three vectors. So first you z-axis, along z-axis. So this is z-axis. The vector is called approach vector. It is denoted as a cap. A cap is the unit vector along z-axis. Okay, and this approach vector, it is in the direction of the end effector moves towards the object. In this direction, the end effector moves to grab. Okay, next along y-axis, the vector which is known as orientation vector. It is denoted as O cap. Okay, so the direction along y-axis, this vector, in this direction, it is also this direction is also known as sliding vector. So actually, in this direction, the end effector, its fingers, the end effector fingers, it can open and close the fingers. So this kind of motion of the fingers, it actually we use them as that motion. We use them as a to hold the object. Okay. The third vector is normal vector, which is in x direction. So this is normal to approach vector and the orientation vector in a right-handed manner. Okay. See, once you look at the description. So let us read this paragraph. Okay. So the z-axis is the approach vector. So which is known as the direction in which the end effector approaches the target or object. And y-axis is the direction of the sliding vector, or also orientation vector O. So in this direction, the end effector, it can open and close the end effector fingers as it manipulates or as it picks the object. And x-axis is the normal vector, which is orthogonal to the approach and sliding vectors in right-handed manner. Okay, in right-handed manner, it is a normal vector. So the product, the scale, I mean, vector product of vector O and vector A. So the scalar product of these two vectors is normal vector n cap. Okay. Okay, so in this way, we need to assign a coordinate frame to the end effector. Okay, so here the end effector, if it rotates about z-axis or approach vector, so that kind of motion is rolling motion. That kind of motion is rolling motion. And when it is the end effector rotates about y-axis or orientation vector, so that kind of motion is pitch. And about x-axis or normal vector, that kind of motion is yaw. Okay, which are similar to wrist motions. Okay. So now let us see the transformation matrix. Transformation matrix for the end effector. So with respect to the coordinate frame of NOA. With respect to the coordinate frame of NOA. Okay, so the transformation matrix for end effector is, so nx, ox, ax, and dx, n by o by a by dy, nz, az, oj, az, tz, 0, 0, 0, 1. Okay, so here you see this 3 by 3 matrix is it represents the orientation of the end effector or rotation of the end effector. So this is the translation vector, and so this is scale type. Okay, so in short form, the transformation vector, it is written as like this. So the elements in this matrix N, O, A, D are the bold letters. So these bold letters are represents vectors. Nth vector, O vector, A vector, and D vector. So D vector is always translation. Okay, so this transformation vector, so in this transformation matrix, the orientation matrix, the 3 by 3 rotation matrix R, which is similar to, so the end effector rotation matrix. So this is rotation matrix for any two coordinate frames, which is equivalent to the rotation matrix of the end effector. Okay, so here in this rotation matrix, so the elements which are scalar product of two unit vectors. Scalar product of two unit vectors. Okay, so nx is equivalent to x bar u bar. Ox is equivalent to x bar dot v bar. So similarly all elements. So now let us discuss the properties of this rotation matrix. Properties. Okay. The first property, the vectors n, o, and a are mutually perpendicular directions. Three mutually perpendicular directions. So hence, so the rotation matrix R, it is called as a orthogonal transformation matrix. So why it is orthogonal transformation matrix? So because the vectors in this matrix are in dot products, are all unit vectors. So it is called orthogonal or orthonormal transformation. Okay. The second property is the scalar dot product of two different columns. The scalar product of two different columns is 0. So that is, for example, nth vector dot product by O vector, O vector dot product by A vector, A product with n is equal to 0. Two different columns. If we multiply them, so the product will become 0. So that third property, the scalar dot product of any column with itself is unity. Say n by n, n multiplied with n, O multiplied with O, A multiplied with A. So the product of any column by its O is unity. And fourth property is the vector product of two different columns gives the third column in the cyclic order. Okay, so n, the vector product of n with O, it gives vector A. O with A, it gives n. A with n, it gives O. So this means that the orientation is completely defined by any two of the three vectors. So the orientation is completely two of the three vectors. So the fifth property, determination of the rotation matrix is always unity. Okay. And the inverse and transpose relations are same as in equation 2.1. Okay, so inverse and transpose relations are, so for example, rotation matrix R1, 2. Rotation matrix R1, 2. So inverse of this matrix, 2 R1. Okay, so this is equal to 1 R R2 transpose. Okay. So inverse of this matrix is equal to 2 R1, rotation matrix of frame 1 with respect to frame 2. And inverse of this matrix also is equal to transpose of this matrix, 1 R2, because here determinant is always 1. Okay. The product of R matrix by its transpose matrix. So this is always equal to identity matrix, identity matrix. So these are the inverse and transpose we have discussed in the equation. Okay. So in rotation matrix, there are 9 elements in total. There are 9 elements in total, which are subjected to the orthogonality constraints. Okay. So only 3 of the 9 elements are independent, or the rotation matrix represented as redundancy. Okay. So you can see in rotation matrix there are 9 elements, which only 3 are the linearly independent elements. Okay. So the elements in this rotation matrix more than the requirement. The rotation matrix has more than the requirement. So such kind of rotation matrix has redundancy. Okay. So more subset elements are involved in rotation matrix. Okay. So that is about rotation matrix and transportation matrix of end effector. So now let us go to the another topic, that is known as the transformation of vectors. So up to now, we have discussed rotation and translation of frames. Rotation and translation of frames. We map them by using the mapping relations. Okay. In the same aspect here, so let us discuss the transformation of vectors. So transformation of vectors, what is vector? So already we have, I told you, suppose so there is a reference frame. So this is a frame 1. Okay. So in this frame 1, so there is a point P. So there is a point P. So how do we describe this point P with respect to this frame 1? Okay. So if I define the position and orientation of this point with respect to this frame, so that is known as the description of a point. So from this origin of frame 1, if you draw a line towards this point P, that is known as a vector. So OP is the vector. OP is the vector from O to P. From O to P. So now, about this vector, let us discuss in this topic. Okay. How it translates in space, how it rotates in space. Another we have to discuss in this topic. Okay. So let us read this paragraph. So in the previous section, so concepts of mapping and the spatial transformation of frames were developed. Okay, we have seen mapping and spatial transformation of frames we have seen in the previous concepts. Okay, so these concepts will now be applied to vector transformations. Okay, so transformation of vectors, rotation and translation is distinctly different from mapping. So where in mapping, the description of a point from one frame to another is changed. So that is the concept in mapping. So there are different situations for transformation of vectors. We have to discuss in this talk. Okay. So first of all, so rotation of vectors. When the vector rotates in the frame, in the space. So let us consider vector 1p, which is rotated by an angle theta, by an angle vector 1p. So the vector 1p and 1q, which are in the same frame, x, y, z axis. Okay, but that vector rotates with an angle theta about a k axis. So that is our case to discuss here. Okay, so the vector 1, 2, it is unknown. We need to find out this vector. Okay, so this is equal to rotation matrix 3 by 3 rotation matrix and vector 1, 2. If this vector is known, okay. So let us look at the figure. We can understand more clearly. So here, here we have two figures. So one is so in this figure, the vector p, the vector OP, it is rotated by an angle theta to the new vector OQ, to the new vector OQ. Okay. So this is one aspect. This is one aspect of rotation of vector from its position, from its one position to the other position. So there are similar kind of motion of vector. So instead of rotating the vector, so here in this figure, instead of rotating the vector P, OP, rotating the coordinate frame in the reverse direction, of the vector rotation. Okay, so see here, minus theta is the rotation of the coordinate frame about k-axis, See, minus theta is the reverse rotation of the vector. So the equation for the vector 1q, it is same. So in whatever way you find out the vector 1q, it is the relations are identical. Okay, so both the figures represent the okay. So the operations involved in two cases, such as in this case and in this case, are identical. So only the viewpoint is different. The viewpoint is different. So mathematically, both are identical, identical representation. Okay. So this allows using the rotational transformation matrices for vector rotations and frame rotations. Okay, so there is no difference of using this rotation matrix R of theta. So here for the rotation matrix, so there are no subscripts and no superscripts. So why there are no subscripts and no superscripts? Because the vector which is in the same frame, so that's why we needed to write the superscripts and the subscripts. Okay, so this is actually we need to write the superscript 1 and subscript 1, but with the same frame, the vector rotation in frame 1 with respect to frame 1, we need to write the 1 1 for the rotation matrix. Okay. చూడండి ఇక్కడ ఒక విషయం అండి, ఇక్కడ రొటేషన్ మ్యాట్రిక్స్ అన్నది మనం ఫ్రేమ్ రొటేషన్ కైనా వెక్టర్ రొటేషన్ కైనా సేమ్ రొటేషన్ మ్యాట్రిక్స్ యూజ్ చేస్తామండి, ఆర్ ఆఫ్ థీటా. ఓకే, ఈ రెండు కేసెస్ లో రొటేషన్ మ్యాట్రిక్స్ ఆర్ ఆఫ్ థీటా అన్నది సేమ్. Okay, so there is no difference. Next, translation of vectors. Okay, so frame 1, in which the point P from O, the P as a vector 1P. Okay, so let us assume this vector OP, it is translated to vector OQ. From this point to this point, this is the translation vector. From P to Q, this is the translation vector. So this is OQ is the another vector, so new vector. Okay, so OP from OP vector, it is translated to OQ vector. The translating distance is 1D. Okay, so for this, so the vector, new vector 1Q, it is unknown. This is equal to vector P plus translating distance 1P plus 1D. So this is this figure, it is one way of representing the vector translation. It is another way of representing the translation of vector. In this so in this second figure, so instead of translating the vector, we translate the coordinate frame from in reverse direction, from x, y, z to the in reverse direction, negative direction. So this is minus 1D. Okay. So this is the translating distance. So this is the new vector. So this is the original vector. Okay. In both the ways, we can find the vector Q. If I know the vector P and the translation distance. So now combined rotation and translation of vectors. Translation of vectors. So consider vector P as shown in the figure above, which is given a rotation of theta about k-axis, followed by translation 1D to get the new vector 2P. So if T is the transformation matrix that describes frame rotated by R and translated by D with respect to another frame. Okay, so here we have vector 1P. It is rotated by an angle theta about k-axis and followed by a translation of 1D to get new vector 2P. So to get new vector 2P, so here is the mathematical relation is T1P. So T1P. So where T is the, again, transformation matrix, 4x4 transformation matrix. So in which R of theta is the rotation matrix, 3x3 rotation matrix, and 1D is the 3x1 vector, translation vector. Okay. So here, T transformation matrix, the frame itself, 1, 1, T1. So 1, here also no need to write the superscripts and subscripts for the transformation matrix. So rotation, let us read this paragraph. Rotation and translation relationship of equation 30 and 2 are same. Okay. So 2.30 equations ante manam intaku mundu coordinate frame rotation translation discuss chesavandi aa equations ee equation same ani manam teesukovali ikkada. So either vector rotation aina frame rotation aina same untayandi, పెద్దగా changes ఏమి ఉండవు. But the direction of u అన్నది different గా ఉంటుంది అంతే. So it can be stated that a vector transformation which rotates the vector by theta and translates it by d is same as the homogeneous transformation T that describes a frame rotated by theta and translated by d relative to the reference frame. So that is the main point in this you have to remember in this topic. Okay. Okay, I will discuss the composite transformation in the next class. Okay, what is composite transformation? So previously we have discussed the transformation between two frames, but in composite transformation we will discuss the transformation between more than two frames. More than two frames. Okay, we will discuss in the next class this topic. It is this topic is also very important. So because in an industrial robot, so there are number of frames from each end of the link. Okay, we need to develop mathematical relation in those number of frames. So for that case, the composite frame transformation is to know the concept of this topic is very essential in industrial robot. Okay. So the topics which are above we discussed last class and this class, which are all basic concepts, are essential to develop the composite transformation. Okay, I stopped here. Do you have any doubts? Please ask now. Raise your hand and ask your doubt. So raise your hand and ask your doubt, or else you chart the your doubt. So anybody, do you have doubts? Emma, మీకు ఏమైనా డౌట్స్ ఉన్నాయని అడగచ్చు. మీ డౌట్ ని చార్ట్ పూర్వకంగా అడగచ్చు. చార్ట్ చేయండి. Okay, or else let us discuss briefly about the today's summary of lecture. Okay, previously, I mean last class we have discussed about the last class and before last class we have discussed about the mapping between the frames, the relation of mapping between the frames, and in today's class and more importantly in the last class we discussed the transformation matrix, okay, which consists of 4 parts: 3x3 rotation matrix, translation vector, perspective transformation matrix, and scale factor. Okay, so in this class I have discussed end effectors coordinate frame, how it is convened, how it is attached to the end effector, what are the different factors involved in this end effector part, and about their coordinate axis, what are the motions which are same as wrist motions, roll, pitch, yeah. The vectors are normal vector, sliding vector, and approach vectors. Okay, and transformation matrix of a for the end effector, which is similar to transformation matrix of between 2 frames. So this is the rotation matrix, which is identical to rotation matrix of end effector. But the elements in this rotation matrix are the scalar product of unit vectors. Okay. More importantly, in this lecture, I have discussed the properties of vectors of end effector. Which are these properties are very, very important. You have to remember them. And transformation vectors. So transformation vector is nothing but similar to transformation of coordinate frames. Okay, but the view we look at the rotation of vector and frame are different, but mathematically the transformation of say. So rotation of vectors we have seen, and rotation of translation of vectors, combined translation and rotation we have discussed. So this relation is similar to that transformation matrix of two frames. Okay. So these are the topics we have discussed today. So in the next class, we will discuss the composite transformation. Thank you very much. I'm leaving the meeting.